Welcome back, everybody. We're doing some more Taylor series stuff today. Um, Last time we were thinking about what it looks like to center a Taylor series somewhere, and in particular, centering it somewhere other than zero. We did an example with natural log of x and computed that Taylor series centered at 6 and found its radius of convergence using the ratio test. Fair bit of work in doing those two steps there. We got through it. And again, the idea with what it looks like to center a Taylor series at a particular value is that gives us kind of the anchor for where our polynomials are going to kind of spread out from. Today we're going to be switching gears a little bit and essentially making use of this selection of functions that we know power series for. And we're going to use them to help us integrate. This essentially becomes a new kind of integration technique, right? And well, what power series do we know? Well, here, let me switch over to the stylus. The first one that we came across was 1 over 1 minus x, right? That was our one that equaled the geometric series. We use that to help us figure out the power series for inverse tangent and also a natural log of 1 plus x. We related both of those, right, to this 1 over 1 minus x using a differentiation, then integration to go back. Since we've been in the pure Taylor series land, we figured out Taylor series for e to the x and sine of x and cosine of x. All right, so we have this kind of a grab bag of functions that we know Taylor series for, and we can use these to help us integrate by taking the function that we want to integrate and writing it in terms of a power series. Because a power series, right, at the end of the day, is really just an infinite polynomial. And polynomials are real quick to integrate, right? Just term by term using the power rule. And so that's sort of the idea, is that we can integrate by writing our function as a power series. And so here we're just going to work through a few examples of doing that. So each one, we're going to want to evaluate the integral using known power series. So kind of use these known power series to help us out. And so for this first one, we're integrating e to the minus x squared dx. And we're going to want to write our answer in standard form. Maybe the first thing to talk about with this, and I'll pause in just a moment and give you a chance to work through this, but first observation is, well, hey, do we really need power series to work this out? And well, if we think about our techniques so far, there's really not a nice way to algebraically mess with this. And u sub doesn't seem very hopeful because the derivative of our inside function, negative 2x, is not really floating around out here. If we had an x out front, then we'd be in business. U sub would be good to go, but that's not going to work. And really, the other techniques that we'll learn later in the semester as well in chapter 7 aren't going to help out here. And actually, this function, e to the minus x squared, is actually just totally impossible to integrate this using what we call elementary functions. So none of our techniques are going to work. If we're going to want to come up with an integral for this, we're going to need to move outside the realm of somehow like, quote, ordinary functions. And here we can use power series, or infinite polynomials, as a way to integrate this. All right. The second thing that we might notice is that, well, this function, e to the minus x squared, is not literally e to the x, but it's kind of close, right? It's e to the something. And we can use that, right? We know the formula for e to the x, right? That's the sum from n equals 0 to infinity of x to the n over n factorial. Right, that's how we write e to the x as a power series. If we want to think about this formula in a general way, right, the way to read this formula, this x is just a placeholder, telling us, well, that e to the whatever is the sum of that whatever to the n over n factorial. So we can read it like this, right? E to the box is the sum of box to the n over n factorial. And so here, well, what's going to be in that box? Well, it's this exponent. Right, so that is going to be what we can feed into our box over here. Okay, so all of that, though, is really just starting on step 1 of the plan. So if we're wanting to integrate this function, step 1 is to actually take the function that we want to integrate and write it as a power series. And then we're going to want to get it in standard form so that we can integrate. If it's not in standard form, things are going to go wrong when we integrate. All right, so first step here is actually kind of writing the function as a power series. And then once we've done that, we can go ahead and integrate that infinite polynomial, right, to find the integral that we want. All right, so we have a 2-step plan for success here. Why don't you pause the video, take a few minutes, and see if you can work through this. Use this general way of thinking about our formula. Try and write our function here as a power series and then get it into standard form. Once you have that, go ahead and integrate. All right, well, let's talk through this one, see how it goes. So here, if we, in our box here, plop in what we have, the negative x squared, then this is how we can write e to the minus x squared as a power series. So I have it written a little bit nicer down here. And so here, that minus x squared gets raised to the n. And now to get this in standard form, we just need to break up this stuff, get the x stuff on its own. And so this minus, right, the way to think about that is as a minus 1 times this x squared. And this exponent n does distribute nicely over this multiplication to the minus 1 and to the x squared. And so we get minus 1 to the n times x to the 2 to the n, and x to the 2 to the n is x to the 2 and x to the 2 to the n equals x to the 2n, right? That's the idea going on there. All right, and so now we are in standard form, and we're happy about that. Right, because that means that we can integrate at this point, right? And so, and the idea here is if we want to integrate this, gotta remember what this bunch of symbols means, right? This is telling us that we're adding up a whole bunch of terms, infinitely many, and each term looks like this, right? And for each term, the n is set, right? It's gonna be n equals 0 at the first one, n equals 1 at the first, n equals 2, and then n equals 3. Then we'll have the n equals 4 term. And at each term, this n will be constant. So in terms of integrating, right, this minus 1 to the n, that's going to be a constant when we're looking at a particular term. And this n factorial is going to be a constant. And so this thing in green is actually just a constant multiple attached to this power of x in each term of our power series. And so to integrate this, we're just going to completely ignore our constant multiple here, and we just need to hone in on this x to the 2n and integrate that. And the way we do that is like any other power of x to anti-differentiate. Right, we're going to add 1 to the exponent and then divide by our new power. And so if we start with 2n and we add 1 to it, we're going to get 2n plus 1. And then if we divide by that new exponent, we'll have 2n plus 1 in the bottom. And so here's what we end up with. Here's the antiderivative that we just talked through. Right, we have that green constant multiple still staring back at us. And then over here, right, this is where we computed the antiderivative of our x stuff. And right, normally when we're doing just indefinite integrals, right, the thing to remember is, the little thing to remember is that we wanted the plus c, right? The integral of x squared is x cubed over 3 plus c, because when it's indefinite integral, we're asking what are all the antiderivatives to this function, and so the plus c gives us all of them. We could technically write the plus c on the right. It just looks a little bit awkward because it looks like we're maybe adding it up, and so just for visual cleanliness, we write it on the left as c plus instead of plus c at the end. All right, but same idea. All right. So that's example 1, how we can use power series to write our function as a power series and then integrate. Let's look at our second one. All right. So here, the function we're integrating is x times cosine of x cubed. And once again, right, if we look back at the bag of functions that we know power series for, this isn't one of them, right? But right, the cosine, right, that should grab our attention. We know a formula for the power series for cosine, and so we should be able to use and adjust that formula in order to write our function as a power series. Again, we want to get that in standard form. And once we have that, we're good to go to integrate. And so just as a nudge, and here is the formula for cosine of x. And so again, thinking about this in a general way, this is telling us that cosine of something is all this stuff with that something raised to the 2n power, right? All right. So at this point, pause the video and see if you can use this general formula to figure out how to write. You could do it in 2 steps if you wanted, cosine of x cubed as a power series, and then multiply that by x, get that in standard form, and then integrate. All right, let's talk through it here. So using our formula here, right, if we have a x cubed inside, then that's what gets raised to the 2n. And like in our function, if we have an x out front, well, then we're just going to have an x out front here, and we can see that down here. All right, so right here, this is kind of an ugly way to write our function as a power series. It's not in standard form yet, though, so we want to do a little bit of work. For starters, let's deal with this x stuff. Right, x cubed to the 2n. Those powers are going to multiply, get 3 times 2n, or in other words, 6n as that exponent. Next, let's deal with the fact that we have this x hanging around out front, and let's distribute that in, right? Just bring that inside the sum, and actually we can bring it, if we want, just all the way inside and kind of plump it right here next to the x. There it is. And if we have 6n x's hanging out right here, multiply one more, that's just going to add 1 to the exponent, right? If you want, the exponent here is 1. And so rows of exponents, those will add. And so at this point, through our work, it says this thing is in standard form, which makes us happy because we are now all set to integrate. And once again, this alternation and the factorial on the bottom, for each term n that we are looking at, that's going to be a constant. And so we're just needing to integrate this power of x here. So we'll add 1 to the exponent, get 6n plus 2, and then divide by that 6n plus 2 new exponent, right, to integrate. All right, so there we go. Here's our power series. Integrating gives us this power series right here, and then just the plus c for all antiderivatives to our function here. So these first two integrals, we've been getting our power series in standard form. This next one, we're going to get a little bit more practice working this out in expanded form. This should feel pretty similar to the natural log integral that was the last problem on our written homework, our recent written homework. Okay, let's see what function we're dealing with here. So here we have e to the x minus 1 over 3x as our function we're wanting to integrate. Here we're wanting to write our answer as an expanded sum. And so along the way, we'll essentially just want to use our formulas in their expanded form. And so our plan is the same as it's been thus far. Step 1 is just take our function and write it as a power series. And once we have that power series, we can go ahead and integrate it. And now here, the way our function is built, with this minus 1 in particular, it's going to be useful to build this up in stages. So what I'd encourage you to do is, in terms of writing our function here as a power series, start with writing e to the x as an expanded out power series. Then incorporate the minus 1 into that. And then afterwards, we'll divide what we have by 3x. Kind of do a 3 steps to get that power series. And what I mean by kind of working with our formulas in their expanded form is like this, right? Again, our formula for e to the x is right here, in the standard form with summation notation. But written out in expanded form looks like this, right? Here on the left, here's our n equals 0 term, n equals 1, n equals 2, n equals 3, n equals 4, and so on. So here's our nice expanded form, how to write e to the x as a power series. And so we'll want to start working with this. And so at this point, pause the video, see if you can take this formula, see what we get when we subtract by 1, and then divide by 3x. And once you have a power series with the dust all settled, go ahead and integrate. All right, let's see how this one goes. The thing to remember is, so if we want to subtract 1, we only want to subtract 1, 1. And so what I mean here is, if this is e to the x, well, if we then want to subtract 1, well, we only want to subtract 1 from the right-hand side. We don't want to subtract 1 from every single term. That would be like subtracting infinity or something like that, right? It wouldn't be balanced, right? We just want to subtract 1 on the left, and so we just want to subtract 1 on the right. And so notice what happens is that just this very first term gets killed off, and what's left is just all the other stuff. And so we see that here. All right, so now let's think about dividing by 3x. And I think the clean way to think about that, if we pull out this 3x as a 1 over 3x multiple on our e to the x minus 1, hopefully things are a little bit more reasonable feeling with our algebra here. And so here, let's take e to the x minus 1 and swap that out for this power series that we know it equals. All right, now this 1 over 3x, it's multiplied on this big old sum, right? And so essentially, just like we would if this was a finite sum, this 1 over 3x is going to distribute to every term here on the right. All right, so if we could see them, they distribute to all of those as well. And so what we end up with, x over 3x for the first one, x squared over 3x 2 factorial, and then 3x and 3x again in the denominators, right? So those all go into the denominators. But at this point, we can do a little simplifying, yeah? So our x's cancel off here, and we're just left with the 1 up top. This x will cancel off with one of these, and all of our numerator powers of x will just drop by 1. And so at this point, it's kind of perhaps easy to lose track with all this work that we've been doing, all this writing, where we're at in terms of our game plan. At this point, we're done with step 1, right? We've taken our function that we want to integrate, and we've written it as a power series, right? And so we're happy with that. Step 1 is complete, but we still have step 2 to go, and so we need to integrate this thing, right? But we integrate our infinite polynomial here, just like a regular polynomial, right? Per our calculus for series theorem, we just go ahead each term and integrate. So 1/3, this constant becomes 1/3 x. Then here this x becomes x squared over 2. This x squared becomes x cubed over 3, x to the 4th over 4. And so integrating here, we get this as our result. And so notice here we get the 1/3 x, and here the x squared, and then I just popped the 2 right here up front, x cubed over 3, x to the 4th over 4, and right there, there's our nice single antiderivative. I just realized I forgot plus c. There we go. There's all of the antiderivatives now. All right, well, good work today, everybody. If you have any questions, post them on Piazza, and I'll see you next time.